Have you ever wondered how we actually put a number on the world around us? How we measure things? Well, that's exactly what mensuration is all about. It's the mathematics of measurement. It's kind of like the hidden language that describes everything, from the very screen you're looking at to the room you're in. So let's break down how it all works.
Just take a second and look around. Everything you see has a shape, a size, some kind of dimension, right? So, how do we translate all of that into cold, hard numbers? That's the big question we're going to tackle. And the answer? Well, it starts with a simple definition.
So there you have it. Officially, mensuration is the part of geometry that's all about measuring length, area, and volume. And to really get a grip on this, we've got to start with the most fundamental building block of pretty much every other shape out there.
That's right, the humble triangle. It might seem basic, but here's the secret. Almost any other shape you can think of can be broken down into a bunch of triangles. If you can understand this one shape, you've basically got the key to unlocking the rest. And this is the one formula you really need to know. For any triangle, anywhere, the area is just 1/2 of its base times its height. It's simple, it's elegant, and it is incredibly powerful. But what's really cool is seeing how this one rule cleverly adapts for different kinds of triangles. So check out these special cases. For a right-angled triangle, the two sides that make that 90-degree angle, they're basically your base and height already. And for equilateral and isosceles triangles, yeah, those formulas look a little complicated, but trust me, they're just smart shortcuts that all come from that one universal rule we just talked about. Okay, so where do we go from here? Once you get triangles, you can start piecing them together to build bigger, more complex shapes, like quadrilaterals, anything with 4 sides, and from there, basically any polygon you can imagine. And this is a perfect example of what I mean. The area of a parallelogram is base times height. But why? Because it's literally just two identical triangles stuck together. So when you add their areas, half base times height plus another half base times height, you get one whole base times height. See how it all connects? It's pretty cool. And here are the go-to formulas for other common 4-sided shapes. A rectangle is just simple length times width. A square is just a special kind of rectangle, right? A rhombus and a trapezium have their own unique formulas, but at their core, they all rely on the same idea of breaking the shape down into simpler pieces. Okay, now for what I like to call the power tool of geometry. A regular polygon is any shape with equal sides and angles, like a pentagon or a hexagon. Now, this formula looks intimidating, I get it, but think of it like an incredible multi-tool. You don't need to memorize it, just appreciate that by plugging in n, the number of sides, you can find the area of any regular polygon. But wait, what about a shape that has no straight sides at all? The circle. It's in a class of its own, totally different from polygons. It's defined by one single perfect curve, and its secrets are all unlocked by one of the most famous numbers in all of mathematics. And of course, that number is pi. The two essential formulas you need for any circle both use pi. The circumference, that's the distance all the way around, is 2 times pi times the radius. And the area, all the space inside, is pi times the radius squared. Simple, but absolutely fundamental. So how can we actually use this? Let's try a practical problem. Imagine a circular road, like a roundabout. All we know is that the outer edge is 44 meters longer than the inner edge. The question is, how wide is the road itself? It sounds kind of tricky, but the answer is surprisingly simple. The width of the road is exactly 7 meters. So how do we get that? The key is realizing the road's width is just the difference between the big outer radius and the small inner radius. And since we know the difference in their circumferences is 44, we can use that c equals 2 pi r formula to work backward and figure out the difference in their radii. It's a clever little puzzle solved with just one formula.
All right, so we've gotten a pretty good handle on flat 2D shapes, but let's be real, we don't live in a flat world. So let's add a third dimension, height, and jump into the world of 3D objects, the ones that have volume. Just look at this comparison. On one side, you've got a flat rectangle. It's got 2 dimensions and area. On the other, a cuboid. Think of a shoebox. It's got 3 dimensions and volume. So what's the big idea that connects them? What's the secret that turns flat area into 3D volume? This is it. This is the big aha moment. To get the volume of most regular 3D shapes, all you have to do is find the area of its flat base, and then multiply it by its height. You're basically taking that 2D area and just stacking it up layer by layer to create a 3D object. And you can see exactly how it works right here. For a cuboid, the base is a rectangle, right? So its area is length times width. Multiply that by the height, and boom, you've got the volume. For a cylinder, the base is a circle with an area of pi r squared. Multiply that by its height, and you have the volume of the cylinder. It's the exact same principle, just with different base shapes.
So, we've got the theory down. Now let's really put it to the test with a real-world problem that pulls a few of these ideas together. This shows how mensuration isn't just for textbooks. It's a practical tool for everyday situations.
Okay, here's a classic problem. We've got a big rectangular garden, and there's a path running around the inside edge. How do we find the area of just the path? Well, the logic is actually pretty straightforward. First, you get the area of the whole garden, 80 times 60, which is 4,800. Easy enough. Next, you find the area of the garden without the path. Since the path is 4 meters wide on all sides, the inner part is 72 by 52, giving an area of 3,744. So the final step? Just subtract the small area from the big one, and you're left with the area of the path, 1,056 square meters.
We've covered a ton of ground, from the simplest triangle all the way to the volume of a cylinder. But the real goal here is to start seeing these shapes everywhere. So seriously, look around you right now. Your phone or monitor is a rectangle, that can of soda is a cylinder, the room you're in is a cuboid. Once you start looking for it, you'll realize our entire world is built from these simple, measurable shapes.